Hello, everybody. I hope you hear me well. My name is Denisa Mailatova from SOS Electronic. I'd like to welcome you all at our webinar with Wiznet company. Wiznet is our long-term partner and a supplier of SOS Electronic. The company is focused on internet communication. Our host for today is Mr. James Kim, Director of Wiznet. You have had an opportunity to see his previous webinar in June. Current webinar, we call it Deep Dive, and we would like to talk about serial to Ethernet more in detail. If you have any questions during the webinar, please write them down to chat or Q&A. Don't be afraid, we all are learning by asking. You can do it during the webinar anytime. James will answer them after the presentation. And now, James, please, you can start your presentation. We are eager to learn something new.
Okay. Thank you, Denisa. Hello, everybody. This is James from Wiznet. This is our second webinar about serial to Ethernet, Wiznet serial to Ethernet solution, and we'll go over core details this time. That's why the title of this webinar is Serial to Ethernet Deep Dive. First, we will look at what functions our serial to Ethernet modules provide and go into details about how its function is implemented. Witness the serial to Ethernet functions to control the Ethernet connections like such as the TCP client, TCP server, TCP mixed, and UDP, and also control the settings of a local network and remote network configuration. You must be able to set a serial interface in order to use Wiznet's S2E, like baud rate, flow control, and serial data packing condition, and so on. And remote operations are available. You can device search and setting remotely, and firmware upload and reboot, factory reset remotely. This slide shows the various settings and options of Wiznet S2E. The functions are categorized into 6 parts: operation mode, user SIO, network settings, and network options, serial settings, and serial options. Please refer to the previous webinar, Serial to Ethernet Bootcamp, for more detail about the meaning of each options. The development environment for Deep Dive is based on Eclipse IDE tool and GNU ARM embedded toolchains. As a hardware platform, we will use the Wiznet 750SR TTL EBB. You can see that the view of, on the right upper side on the screen. When explaining internal structure and the working flow, we will check it with the real codes. So we need the source code. In this section, I will explain the process of importing the real project into Eclipse IDE to review source code. This is the code memory used by Wiznet, the Wiznet 750SR standard firmware. Among the total 128 kilobytes of flash memory, 28 kilobytes is allocated for boot, and 100 kilobytes is allocated for application. Both are implemented in 2 different projects, boot project and application project. Although it is not depicted here, we have 512-byte data flash to store the configuration information, such as MAC address, local IP address, remote IP address, local ports, remote ports, and working mode, and so on. The boot code for Eclipse IDE is available on GitHub at this URL. I recommend you fork or download it for your practice. For this webinar, I have already downloaded the project on my disk. This Eclipse project is for with 750S application. You can download it from here. And feel free to fork this as well. This project is also already downloaded for today's review. For the code review, let's import them to Eclipse IDE. Only open Eclipse and select File and Import menu, and select General and existing project into Workspace menu on selected dialog box, and click Next. Then you should select the folder where you downloaded the project as a root directory, and import both with the 750SL app Eclipse and 750SL boot Eclipse folders into the the Eclipse IDE. Let's try it. This is an Eclipse IDE. Import the project. I choose a file and import, and I select the general and existing project into Workspace menu. When I click Next, I have to choose the root directory. So I downloaded these two projects into Webinar Workspace. So I choose this one. There are three projects. I will import this later, and this one is with 750SL app Eclipse, and the below is the boot Eclipse. I import them. No. The Eclipse is importing two projects still. Okay. I will go with the PPT file. To see this project built well, let's try to build binary. At the moment, this is still important. Okay, everything is everything done. So I will try to build the project. Click the project, the title of the project, and then click the right button of mouse and select the build project. Oh. I need to clean project first. Then choose build project. It is in process of building, going well. Sometimes it shows the warning message, but it doesn't matter. Yeah. Almost finished. It finished. So it made with the 750SL app Eclipse.bin file. The size is the 5-6 kilobyte approximately. So you can see the binary file in the default debugger folder here. So they are built successfully. Well, I will start explaining the internal working flow of Wiznet S3 converters from now. Here I'll explain about the boot and application. To distinguish boots from ISP boot code, I will call it app boot. So this app boot and boot is the same things. The reason for the division into two areas of app boot and app application is to perform firmware update using Ethernet. App boot is a supervisor area to manage the firmware updates, and application is where actual serial to Ethernet application code is. When power on, the app boot is executed. System initialization is done, and network initialization is executed for the communication between PC application and serial to Ethernet converter via Ethernet. After that, if application code exists, it will jump to the application area. Then the application code will be executed. If there is no application code, or if it is in process of firmware uploading, or if the app boot mode is running manually, it stays in app boot area and receives and processes the computer message infinitely. Once it jumps to the application area, it again initializes the system and network parts. While running in infinite loop, it processes the computer message and executes the application code, like the exchanging data from between the serial and the Ethernet part. If a firmware upload request message is received while processing configure messages, it jumps to the application app boot, and in app boot, it receives a new binary file from peer system and overwrite a new binary data onto the application code area. This is the process mechanism between app boot and application of a Wiznet 750SL S2E. Next, this is the structure of a Wiznet 750SL firmware source code folder. The firmware source code consists of MCU independent folder and the MCU dependent folder. MCU independent folder includes callback, configuration, I/O library, serial to Ethernet folders. This folder, the codes in these folders are independent to what we use, what MCU we use. The MCU dependent folder is a platform handler folder. It contains code for setting up and initializing the MCU specific peripherals. Flash handler for initializing flash memory. GPIO handler related to GPIO initialization and settings. Timer handler, UART handler, and others are all MCU dependent codes. Now we'll see the top-level working flow of the application. The follows are what the main function of the application code process. First, it starts with initialization. This includes initialization peripherals like a GPIO and UART, and loading configuration data, and doing TCP/IP core initialization and network initialization. Then it repeatedly calls two functions, do SEGs and do SEGCP. Do SEG is the serial to Ethernet convert function, and do SEGCP means control process, so command process. So this means that this is the function that processes the configuration messages to control the serial to Ethernet converter. The detailed structure will be explained after. Now, let's take a closer look at the infinite loop in main function. Besides performing the 2SEG CP and the 2SEG, it checks pairing And the DHCP run is called to update the DHCP status in case DHCP mode is set, and make a ring buffer flag clear when the ring buffer is full. This is the detail of do SCG. Do SCG is divided into 4 cases depending on the working mode. Working mode are TCP client mode, TCP server mode, TCP mixed mode, and UDP mode. The TCP mode uses the connection-oriented TCP socket, and UDP mode uses a connectionless UDP socket. Each function has the same role, except that the connection management is different. By calling UART to either and either to UART, the received data can be transferred from Ethernet interface to UART interface, or vice versa. At this time, depending on the various options you set, you can decide whether to process the data or wait, like the data packing condition. Also, since this device could be used in time-critical cases in industrial area, various flags related to the timer are processed in timer IRQ handler. SCG timer millisecond is called average millisecond, and SCG timer sec function called every second. These flags are related to millisecond basis. This indirect inactivity time flag is related to second base. Let's see the inside of do SCG with the source code. Do SCG is in SCG.c of serial to Ethernet folder. So it's source serial to Ethernet folder and SCG.c file. So you can see do SCG file of functions. It is simple. Do SCG is very simple. This is for debugging, and this is main control of do SCG. It check the operation mode is, if the operation mode is gateway mode. If so, to check the working mode. So there are four cases: TCP client mode, TCP server mode, TCP mixed mode, and TCP UDP mode. And it has corresponding functions: proc SCG TCP client for TCP client mode, and proc SCG TCP server function for TCP server mode, and this proc SCG TCP mixed mode for TCP mixed mode, and proc SCG UDP for UDP mode. This flow chart describes how to manage connections for each working mode. In TCP client mode, connection management is performed with 4 socket status: sock init, sock established, sock close wait, sock closed. New socket is opened by calling the socket functions in sock closed state. The state of socket become sock init if a socket is created normally. During the state of sock init, the connection function is called to attempt to make a connection. because it is in TCP client mode. The state of a socket is automatically changed to the SOC established just after the connection is established. In SOC established status, U2E, UART to Ethernet, E to U, Ethernet to UART functions are called to exchange data between the Ethernet and serial part. When the peer system closed the connection, the status becomes to SOC closed await. If there is unprocessed data in RX buffer on the Ethernet side, it transfer down to the serial and call disconnect to make a socket status to SOC closed. Then the socket state will change to SOC closed, and socket function will be called again for the next session. So in TCP client, socket status is changed from SOC closed, SOC established, and SOC closed wait. And data exchange is done in SOC established status. In TCP server mode, if the socket is created during the SOC closed and the listen function is called to listen a connection request from the peer system. Then once the connection succeeded, the status changes to SOC established. The U2E, E2U function called to exchange data. In TCP mixed mode, the module first operates in TCP server mode. Hence, if the serial data is received before connection, it closed socket and then attempt to make a connection to the specified server by calling connect. When it connects, data exchange is performed like others. When the connection is disconnected by the peer, it is put into the listening status as a TCP server, because TCP mixer mode is, the default mode is TCP server mode. In UDP mode, it calls socket in SOC closed status. Then it turns to SOC UDP status. So UDP, U2E and E2U functions are performed. So you can see that there is no difference except managing connection in all four working modes. Now let's see the dual SEG-CP function. Serial to Ethernet commands, we call it the SEG commands. These commands can be received from 3 different sources: UDP configuration socket, TCP configuration socket, and UART serial interface. It calls proc SEG-CP UDP function to see if any SEG commands has been received from UDP configuration socket. Next, call proc SEG-CP TCP function to check if the SEG commands are received from the TCP socket. And then, when operating mode is AT mode, AT mode means is AT command mode. From the data from serial commands, serial interface is treated as command in AT command mode. So when operating mode is AT mode, it call proc SEGCP UART to see if there are SEG commands from the serial interface. It performs the corresponding operation according to the commands. Then it will perform some special operation like a factory reset, save any changes into flash memory, and firmware upload and reboot. If some of these commands are included in serial commands. A serial to Ethernet converter has various options depending on user situation. We use variables of a special data structure to specify which operations are selected. These setting values should be saved in non-volatile data flash memory, so it can be maintained even when power off. With 750SR can use its external ESCAP-ROM optionally, so you can store options into ESCAP-ROM instead. When power on, the value of the relevant data flash memory is read, and the variable for the device configuration is updated with them. During the initialization process, UART setting, network initialization, and working modes are set depending on each value in the variable. The value in the data flash and variables will be updated if the option is changed by SEG command. This page is about the structure of the variables that stores the setting values. At the far left, dbconfig is a variable that stores all the settings and is composed of 249 bytes in total. This variable consists of substructures such as network info common, network info, serial info, options, firmware update, and user IO info. Network info common stores information of MAC address, local IP, gateway, and subnet mask. Network info contains information which can be changed by each channel. Channel refer to a pair of the serial and the socket, Ethernet socket for data communication. This includes working mode. Current state, and remote IP address, local port number, remote port number, and data packing conditions, and so on. And serial info may also vary depending on the channel as well. It includes baud rate, data bits, parity bits, stop bits, flow control, DTL, DSR enable. Options includes information about the password for TCP connection and the password for search operation, and whether the TCP enable or the DNS mode enable. Firmware update contains information which are useful for the firmware updates. Firmware upload status, and the port number for firmware upload, and the binary file size for two firmware upload. You can revise this data structure and the data flash if you need additional options. This is just for standard firmware. By now, I explained the structure of Wiznet 750SR firmware. Now, I'd like to show you a customization example for your better understanding. This customization example is to monitor the value of user I/O port periodically. Working scenario is like this. The device will work TCP client mode. After the device connects to the TCP server, it periodically checks the status of a specific user I/O port and send it to the server. Data is in JSON format and includes device name and port name and device name and port name and its value, high or low. Device name is consists of device name and the MAC address of NIC. In this example, the standard boot and the standard application code are used as is to make a network firmware update available. If you use our standard boot and application as your base platform, then you don't need to consider how to make your device able to do remote configuration and remote firmware update. Here, I just need to modify some little parts of functions to satisfy the user demands. First, I'll copy base project folder into another folder, then change its folder name to with 750 app Eclipse GPIO. I have already prepared an example because it takes a lot of time to edit it during a webinar, but feel free to try it yourself later. Next, import the new project to Eclipse IDE and follow the import process as I did earlier. Let's do it again. Select file, not export, import, and choose general existing project into workspace and click next in browser. This is the folder. This is what I prepared. The name is already uses 750SR app Eclipse GPIO. I click finish. I made this all-to-one close project. Now this is customization example. Actually, let's edit code. Already I edited the code, but I'll show you what I edited. You need to you have to add below code in SEG timer millisecond function in SEG.c. This means its meaning is the if enable event time flag is set, check if event time counter reaches event interval, which is set in advance. Event interval is 5 milliseconds by default. If time data packing condition is set with a specific value, then event interval equals time data packing condition. Then, if event time count reaches event interval, then flag event occurred flag is set. Oh, too much. Next, copy the proc SEG TCP client functions and rename it proc GPIO TCP client. And add the following code in proc GPIO TCP client. This code means when event occurred, this flag is set when the event time or reaches to event interval. Anyway, when event occurred, read the value of the GPIO and then make a message in JSON format and send the message to the peer system and clear the flag. Let's have a look at the source code. SEG, serial to Ethernet, SEG.C, and proc GPIO TCP client. This one was copied from proc SEG TCP client, and I changed just two parts. I make this sentence comment, and I added this code. What I explained just before, the flag, it checked flag event occurred flag, and flag is set. It reads the get user IO value and make a message in JSON form, then send this message to the connected server and clear the flag. Next, modify the do SEG function. Originally, do SEG function called in case TCP client mode proc SEG TCP client. So we needed to change it to proc GPIO TCP client. Do SEG. Now you can see the sentence was changed in TCP client mode. Comment proc SEG TCP client and added the proc GPIO TCP client to call new functions. Now build the binary, then download the new firmware with the configuration tool. Click the name of a project and click right button of a mouse. Press clear project first. Then choose the build project again. Because my system is not good enough, so building time is too slow. Almost finished? Yeah, finished. It may, with the 750 SL app Eclipse GPIO.beam file. Then you can see it in debugger fault. Beam file is made. So I will upload the application by using the compute tool. I run Wiznet computation tool. Yeah. This is a Wiznet computation tool for Wiznet 750SR serial converter. Press device search first. You can see the modules at the right upper corner on the screen. So this computation tool find the 54 it's megabytes 548815. You can see it. The mega address is 548815. The same. So I will upload the new firmware just before I compiled. In GPIO debug this binary. Today, yeah, this is the Korean time. I choose 5. Firmware update started. Please wait. Firmware update complete. The new binary is uploaded. This example will operate as a TCP client. It should be set, operating mode should be set TCP client. And I use local port number 5000, and I set this module's remote IP is 192.168.11.235. There's the my PC's IP address, and the remote port 5000. The message should be periodically sent to the TCP service device as shown in the figure. I will use Hercules Firmware to show that with 750SR is periodically sending data. I learned Hercules as TCP server, and listen port is 5000, and click listen. Connect it, and it send the data, it receives data from our serial converter. You can see the ID, device ID, device name, with the SAMPTSL, and the 548815 is the MAC address, and this is the second GPIO, and its value is raw. When I pressed button, you can see the value is changed to high. And I release the button, the value is changed to raw. So this module is reporting the status of a GPIO pin correctly. Now I finished today's presentation. I'm afraid of the lack of a more detailed due to the short presentation schedule. However, I think we were able to go over the main concept and customization tips of Wiznet SD converter. Hopefully, this webinar was helpful to you.
Well, thank you, James.
Yeah.
I'm pretty sure it was. If you have any questions, you can write them down. For now, I have one question only, and it's from the beginning, that the downloads for Eclipse, like around, I think the 8th page it was. Is it for free, the download?
Hey, please. Yeah.
Okay, so that was the question. We answered it. And I saw some raised hands, but now they are lowered. So in case you have any question, we are still here. And you can also write to us, to SOS Electronic, and I will contact James for the appropriate answers. We will publish them. Also, the recording from this webinar we will publish on our pages. And I'd like to thank you, James, for an interesting
thank you.
and detailed webinar presentation. Also, all to you who joined us during this event and stayed with us. And I'd like to invite you also for our next webinars trainings. We will spread the word on social media and on our web pages as usually. Please follow us and have a nice day. You too, James. Thanks a lot. Okay.
Yeah, have a nice day. Thank you very much.
Bye-bye.
Bye-bye.